So copper 2 chloride is an ionic compound. So you will see the question asking you calculate the formula mass, not calculate the molecular mass. Molecular mass is for molecules like carbon dioxide. That's covalent compound. So formula mass is for ionic compound. So we have 3 ionic compound here: copper chloride or copper 2 chloride, magnesium nitrate, and hydrated iron 2 sulfate, FeSO4.7H2O. So the other one will be 64 plus 2 times 35.5, like that. Of course, you'll be given your periodic table to calculate that. It's not a big deal. So you can get your answer if you do that. That'll be 71 plus 64 or 3.5. So you get the answer for that one. And that is very, very easy for you. It's not a task at all. I've gone through that thing you sent me. There's some questions there that are very, very funny. And like, that's good now. So 64 plus 71, so you have 135. So you can also do the second one, of course, 24. There is 2 there. That will be 14 plus 48, bracket times 2. So you multiply everything times 2 in this manner. So 14 plus 48. The third one, you will do it yourself. So you'll be doing that one yourself. Third one. So 14 plus 48, 62 times 2, 110. 110 plus 24. 110 plus 24. So I have 134. So here I'll be getting 134. So the third one is the one that is very, very important. Can you do that?
Yes.
Okay, so I'll give you
Wait,
iron.
but
Iron is 55.8 or 56. Okay, at your level, they will say 56. So iron is 56. So we'll go for 56. So we have 56, yes. Sulfur is 30.
what about sulfur?
Okay. So 32. Oxygen is 16
Oxygen
times
is
4.
16.
That will be 64. Then that dot is what? Plus as well. The dot becomes plus. Then it is 7. H2O is 18. That's how you do that. 7 times 18. So you now add together. So that should be what? 7 times
That
18.
should be 278.
126 plus 64 plus 56. So 2 what?
278.
Okay. I saw 246 here. 246. Okay. That's about that. So that one is very easy. Now, before we close the class today, we're going to do some examples of how to calculate the relative atomic mass, AR, from the percentage abundance. Now, like I was telling you before, the instrument that is used to collect data for the measurement of relative atomic mass is called the mass spectrometer. The mass spectrometer has the ability to identify the different isotopes in an atom of an element, different isotopes. So the mass spectrometer can identify the different isotopes and can also help us to get the different percentage composition of the isotope. So the mass spectrometer has so many uses. One of the uses is to accurately calculate the relative atomic mass of the different elements. So data from the mass spectrometer for chlorine isotopes show that chlorine has two isotopes. So we have chlorine 35 and chlorine 37. We use the mass number to identify the isotope, chlorine 35 and chlorine 37. Chlorine 35 has a percentage of 75%, while chlorine 37 has 25 as its percentage. This data is obtained from the mass spectrometer. So the first method to do the calculation shows that there are 3 out of every 4 atoms will be chlorine 35 because everything is 100%, but chlorine 35 is 75%, the other one is 25%. So 3 out of 4 is chlorine 35. So we have average of 35 plus 35 plus 35 plus 1 of chlorine 37, which is 25% over 4, to give us 35.5. Therefore, we say that relative atomic mass of an element is the average is what? Is the average of naturally occurring isotope. Average of naturally occurring isotope of an element on a scale where 1 atom of carbon-12 isotope is weighing 12 grams. That is it. So this one is showing us the example of what we call average, number of naturally occurring isotope, average. Then the second method is that out of every 100 atoms of chlorine, 75 of them are chlorine 35, while only 25% of these atoms are chlorine 37. So to do it the other way that is common to all of us is that 75%, 75 over 100 times the mass number of chlorine. So 75 times 35 over 100 plus 25 times 37 over 100. So 75% times 35 plus 25% times 37. Or you simply just do it the way that it is done on your screen now. 75 times 35 in bracket plus 25 times 37 over 100. You get 35.5. That is that. And is it clear?
Yes, it is.
Okay. So this one is very simple. Now let's move on to what I call the mass spectrometer. This is the mass spectrometer. You can see the diagram is like a curved tube, a tube that is curved. Am I correct?
Yeah.
Okay, now there are some things that you must know in the mass spectrometer. Let us start from this side. Any sample that is added to the mass spectrometer must be vaporized. So the initial treatment of every sample that is added to the mass spectrometer, the sample, whether in the solid state or in the liquid state or in the gaseous state, must undergo vaporization. So the mass, after it has been vaporized, is now placed inside the mass spectrometer. The second stage of the analysis of sample is the ionization chamber. In this ionization chamber, there are two things that is very important. We have the positive electrode, and we have the negative electrode, and so we also have the electron gun chamber. Electron gun chamber is a chamber or is a column where electrons are being shot against the sample. The electron that is being bombarded is just one electron. It's released from a hot filament. Electron is released from a hot filament. That electron can only knock off one electron from the vaporized sample. The sample that is vaporized is an unknown sample of a compound or an element. So the electron gun chamber contains a filament, a hot filament that releases an electron. The electron is able to knock off or to remove one electron from the vaporized sample. So the loss of an electron will make the sample to acquire a positive charge. So we call that this chamber ionization chamber, where different samples become ionized because one electron has been knocked off the sample. So therefore, if a sample is M, the sample is bombarded with an electron from the electron gun chamber. Electron is negatively charged. The result is that the sample becomes ionized. So M becomes M plus, like this, plus the lost electron. The one that was shot into it plus the one coming out plus 2 moles of electron, like this. So it's very important. It's a major stage where the sample is only ionized sample that can enter into the other compartment of the mass spectrometer. If the sample is not ionized, the mass spectrometer will not work on it. So the ionization chamber is one of the most important segments of the mass spectrometer. It helps samples to be ionized. It helps vaporized sample to be ionized because it contains electron gun compartment that releases hot electron that knock off one electron. So one electron is knocked off, it becomes an ionized sample. Now pay attention very well. The ionized sample carrying a charge, it has a name. So this, you call it M plus. The M plus represent uh, the mass of the atom. You call it, I said M plus, right? The actual name is called molecular ion. It's called molecular ion. Molecular ion. Molecular ion. So the molecular ion, after it has, then it is now allowed to go through the mass spectrometer. Now it has been ionized when we are calling it molecular ion. Now it goes through the next stage of the mass spectrometer, which is the acceleration chamber. In that chamber, it has an electric field. The purpose of the electric field is to accelerate the molecule, to make the molecule to pick up at a particular speed, to move the molecule at a particular velocity. So at the acceleration chamber, the sample moved at different velocity. The lighter sample will move faster. The heavier the heavier sample will move slowly. Now, while the molecule is moving, the molecular ion peak can break into smaller pieces. The smaller pieces obtained from the broken molecular ion are called fragments. So the M plus or the molecular ion can break and it may not break. Or part of it can break, some of it will not break. No. So the one that is broken, they are more deflected by the time it gets into the magnetic field. So the purpose of the magnetic field is to deflect the sample according to their molecular mass or the fragment of the sample. So the first one, we have the ionization chamber, acceleration chamber, we have the magnetic field where the ionized samples are deflected or the fragments are also deflected. So you can see here at this place where we have the magnetic field, we have the heavier samples less deflected, and we have the intermediate mass. So the fragment, they are not as heavy as the molecular ion. They are moderately deflected, and a larger sample, they experience higher deflection. Then you also see a vacuum. The vacuum is meant to ensure that all the samples analyzed are under the same condition, because it removes the air that's available to ensure that the sample passes through a vacuum or the same similar condition. So that the vacuum form. Then it goes down to a detector. We call it ion detector. The detector can only detect ion, does not detect what I call radical. Radicals are not ionized. Radicals have what they call odd number of electrons. Radicals. Radical, R-A, a radical. Once my laptop is okay, the other one you enjoy it, so that can write very well. So radical are species with odd number of electrons. They do not have charge. Once they are produced, the mass spectrometer cannot identify them. So the mass spectrometer can only identify ion. So we call it ion detector. Ion detector can only identify ion. So once the ion gets to the ion detector, the ions, the molecular ion peak or the fragmented particles, once they get to the ion detector, it is now amplified, and you have what we call the mass spectrum is produced. So we have the mass spectrum produced in a recorder. So the mass spectrum produced can be analyzed further. So you can have, like this one now, we're having there 3 peaks. We're having 3 peaks. What is the meaning of that? The 3 peaks there, I just want to, okay, we have a peak here, we have a peak here, and also have a peak here, and also a peak here. The number of peak that you have in a mass spectrum is equal to the number of isotope produced, or the number of isotope of that atom, of that element rather. So this one is having 3 peaks, meaning there are 3 isotopes of the element. So when it has 4 peaks, it means there are 4 isotopes. When it has 2 peaks, it means 2 isotopes. So the peaks are proportional to the number of isotopes. Number 2, the height of the peak is also important. The height of the peak is also proportional to the percentage of the different isotope present. So the mass spectrometer helps us to get, or help us to separate the molecules we are looking for, or help us to separate the atoms. into its isotopes and their abundance and their percentage abundance. So this slide now is showing us different departments in the mass spectrometer. We have the vaporization chamber, the ionization chamber, acceleration chamber, magnetic field chamber, the ion detector, the amplifier for the recorder. So very, very important. So we can talk about the different stages now. So like I said before, there are 5 stages, vaporization, ionization, acceleration, deflection, and detection. So are you there?
Yes.
Okay. So we are almost ending now. In the next 15 minutes, we'll be ending the class. So, but what you must learn now in the mass spectrometer today is that there are 5 stages. The chamber for vaporization, ionization, acceleration, deflection, and detection. Detection there includes the ion detector, the amplifier, and the recorder. Deflection includes the magnetic chamber. Acceleration occurs in the electric field chamber, and we have ionization chamber where you have electrons from the hot filament removing or knocking out the electron from the sample, and then the vaporization chamber. So very, very important, because they can ask you that. I learned that you'll be doing oral interview after your exam, Abi.
Yes, 4.
So it can ask you any question. And one of them is that how many stages do we have in the mass spectrometer? How many stages? Your answer is 5. And they can ask you, mention the 5 stages. Just your answer will just be vaporization, ionization, acceleration, deflection, and detection. They ask you what happened at the deflection chamber. Just tell me that higher molecules are less deflected. Lighter molecules are more deflected. Or you can say the ions with a higher molecular mass are least deflected. The ions with a lower molecular mass are more deflected. What happened at the ionization chamber? In the ionization chamber, the sample, incoming sample, is bombarded with what? With an electron. And this electron coming at a very high speed has the capacity to knock off one electron. So the molecule become ionized. And the mass spectrometer can only recognize only ionized samples. So there is need for the ionization chamber. And they can ask you, what is the function of the vacuum pump? The vacuum pump is to ensure that there is no any interferent gases or molecule in the sample. It removes everything called air or anything. So it creates an environment devoid of contamination. So the vacuum pump is there to ensure that there is no air, there is no any contamination. It is pure vacuum. That the sample coming out can be pure sample that is analyzed. So vaporization sample is to ensure that whether the sample is solid, liquid, or gas, undergo vaporization before it goes into the ionization sample. What happens at detection? In the detection chamber, there are 3 sessions there. The sample will get to the ion detector to detect the ion. The machine can only detect ion. So the ion, only the one that has been ionized that will be detected. Then the different samples are detected according to their molecular masses. All right. What is the function of the mass spectrometer? It helps us to determine the actual relative atomic mass of different elements. because many elements they come with their isotopes. Another use of a mass spectrometer is that it is used to identify the structure of unknown compound, the structure of unknown compound, and that is under the pure A level, A2 of the syllabus. They cannot ask you that one, but we can just talk it a little bit when we get there. Okay, so vaporization, the gas, liquid, or solids are vaporized before it is being injected into the instrument, and then from there it goes to the ionization chamber. Less volatile solids are preheated so that they can get vaporized. Then we get to the ionization chamber where a molecule or a sample of atom of an element X, okay, is bombarded with a high energy electron, E minus, to give you X plus. That's what we call the molecular ion. The molecular ion has its own peak. We call it molecular ion peak. The molecular ion peak is responsible for the mass of the compound or mass of the element. So once you know the molecular ion peak, you are sure to know the mass of the compound or the mass of the element. So the molecular ion peak is very, very important. The second important reason, or the second important significance of the molecular ion peak, the molecular ion, apart from knowing helping to know the molecular mass of the compound or the element, it is also used to calculate the number of carbon atoms in an organic compound. It is used to calculate the number of carbon atoms present in an unknown organic compound. But don't bother about that, is under A2. So the molecular ion peak has a positive charge. Why does it have a positive charge? The positive charge it has because it has lost only one electron. So two functions now. It helps you to know the mass of the molecule. Two, it helps you to calculate the number of carbon atoms in an unknown molecule or compound. And going from there, once the sample has been ionized and has formed the molecular ion there, then you cannot have what we call fragmentation. As the sample moves through the mass chamber, the mass spectrometer, it hits the side, they collide with each other, so the molecular ion can break into fragments. The fragments are also collected and their masses are also measured. And then the masses measured now, you can from there put it together to know the structure of your known compound. That's about this ionization chamber where the molecule is being bombarded with high energy moving electron. Okay, that's about that. Then we quickly go to the acceleration chamber. This chamber, positive ion, such as the X plus or M plus, are accelerated by an electric field. So there are electrode, negative and positive electrode that provide additional energy to ensure that the ionized sample can move at a particular velocity. Then we have the deflection chamber. That is where we have the magnetic field. The north and the south pole of the magnet are there to cause deflection. So the accelerated ion passes into a magnetic field. As the ion pass through the magnetic field, they are deflected according to their mass. The lighter ones are most deflected, and the heavier ones are least deflected. So the detection chamber, like I said before, if the accelerating electric field and the deflecting magnetic field stay constant, Ions of only one particular mass to charge ratio will hit the ion detector at the end of the instrument. But that is not what happened. The molecule move at different velocity. So ion of smaller mass to charge ratio will be deflected too much. Also, they move at different velocity. The latter one will move faster and they are also deflected. So what are you going to learn under the deflection? Or under the detection? Now the detection, we have the recorder, we have the detection, the ion detector, and the amplifier. The three of them, they work together. So the first one is the ion detector that detects. After that, then we have the magnifier, and then we have the recorder to record the peaks according to their percentage. Then there is an issue here called the mass to charge ratio. The mass to charge ratio. There is nothing, it's nothing more than the fact that when a graph is plotted like this, the x-axis has to do with the mass of the ionized sample, mass of the ionized sample. And in many cases, the charge on the ion is +1. So mass stroke charge or mass to charge is always the mass of the sample over the charge, and the charge is +1. So if the mass to charge is 15, so if the mass is 15, the charge is 1. So 15 over 1 will still be 15. So mass to charge ratio is just the fact for you to know that the x-axis is, we plot that one on the x-axis, and it's usually written mass to charge, M/E. And from there you will see different peaks to show. Then we have the y-axis. The y-axis has to do with the percentage abundance of the different isotope in the molecule, the abundance of the sample. Okay, that's about that. So we'll be stopping here today, but this is just an example. This is where we're going to stop because we have spent full 2 hours now. So we'll stop here. This will stop on this slide. Then you will see this slide now. You will see this place. Look at this one. This is a graph obtained from the mass spectrometer. And then you will see 3 peaks. One of the peaks is 90.92% of neon 20. And we have another peak, very small peak, 0.26% of neon 21. And we have another peak of 8.82 of neon 22. So there are 3 isotopes. This means there are 3 isotopes of neon. The one that has the largest abundance is neon 20, 90.92%. So these abundances are used to calculate the relative atomic mass of elements. So in doing that, when look at this one, calculate the average relative atomic mass of neon using the above information. So out of every 100 atoms of neon, 90.92 are neon 20, 0.26 are neon 21, and 8.82 are neon 22. Using that, you can have 90.92 times 20 plus 0.26 times 21 plus 8.82 times 22 over 100 to get your answer as 20.18. It's always decimal because it is obtained from average of different isotope of the element. Okay. Do you have question?
No, I don't.
Okay. I'm going to send you some question on how to calculate calculation of relative atomic mass from the spectrum here. I mean the spectrum of the graph here, that you can learn from there. So we will meet. When are we going to meet again now?
It's up to you.
When?
It's up to you.
Okay. That'll be Tuesday next week, right?
Yes.
Okay. So I will send this slide to you as well. But I will first and foremost, I will send a question to you that you can also calculate. I will send other questions as long as the one that we have covered, that you can learn more. So I wish you all the best. Enjoy
Thank you.
yeah. My regards to your mommy, and
Okay, sir.
enjoy yourself. Bye bye.
You too. Bye.
Bye.